Hello, everyone. Please make me host. Yeah, thank you. Please make me host. Please make me host. Hello, audible.
Yes, sir.
Hello. Yes, please. So let us today. This is the marathon lecture, means 4 hours lecture. Okay, we take a break in between. If required, a tea break. But today is we solve like this 2 questions from power electronics. Then we have a week revision of old question papers. So this question, explain what is the mean by terms wave, frequency and average value. Okay, so when we compare this AC and DC, okay, so with respect to T, this voltage or current of DC is constant here. So it is a VDC. So your direction is always positive, and constant value it is also. So this polarity and magnitude is constant with respect to time. But when we see this AC, okay, this is T means omega T time period, okay. So this is positive, this is negative. So this your voltage or current waveform are very altered, correct? So your direction it is positive, otherwise negative. And see magnitude is also changed at T1, T2, T3. At different time, it is different value. Okay, like this V1, V2, V3. V1, V2, V3. Correct? The maximum value, this maximum value occurs at this T4 time. Like it is, 0, then it is a pi. So here it is pi by 2, 90 degree. This value is occurs as a peak value, Vm, maximum value. So this value of V with respect to T we draw, same like. Then this positive and negative cycle will make a one complete cycle. Positive half cycle and negative half cycle. Combinedly they make a one, it is called one cycle, alternate. Then the time taken to complete that cycle, it is called period of wave form, okay, time period. And then if we calculate the frequency, it is 1 by time period, means it gives you cycles per second. That is called as a frequency, okay. The frequency of alternation means it change. Positive to negative means this number of cycle completed in a unit time, that is called frequency. Number of cycles completed in unit time, that is called cycle. So this is the cycle, it will cycle per second, or it is hertz frequency. Okay, then waveform means what is the waveform? Variation of your magnitude. Okay, variation of this magnitude with respect to time, that is called a waveform. Then their average value. So we see different values. We can calculate the average value. Means suppose these are the individual values. If we calculate the average of this, we get a this. Okay, this value is called average value. Average value. Okay. See, AC values generally different values of AC voltage or current also. What is the values which are defined for AC? For like first is instantaneous. Instantaneous values, okay? Like that is V1, V2, V3. These are the values at time T1, T2, T3. So this is real time value, okay? Then peak value. Okay, it is a maximum value attained by where the voltage or current wave correct current or voltage waveform, that is the peak value. It is denoted by these are this V1, V2. Now this peak value means maximum value. Okay, this. Then we calculate the average. Average, it is V average. What is the average? We take an average. How we calculate the average? Average value. This is maximum value. Now average. So see how we calculate average. Suppose we have to add this all values like V1 plus V2 plus V3 plus up to Vn number of, then divide by integer T1 plus T2 plus T3 up to Tn. This, okay. This is called, we can calculate average value. Now this here it is difficult to add this all the real values. So what we do? Always if the curve, then if we integrate from 0 to pi, okay. So it is give integration means summation. So it is 0 to pi v d omega t. If we integrate, so it gives you summation. Then divide which time period is. Actually, we calculate average from here to here, up to here. If we integrate from here to here, we get a 0. That's why we can calculate average up to this half cycle. Okay, average up to half cycle. Then we double that value. If into 2, the average is t. Okay, this. So this is the average value. Now if you put 2 into 1 by 2 pi, 0 to pi up to here, t is 2 pi, okay. Then integration of v is, what is the equation for this? Vm sin omega t. And if we put here Vm sin omega t, Vm sin omega t, d omega t, 0 to pi. My dear, this 2 cancel, it is 1 by pi. And you know, Vm is constant, it comes outside this. Then you have to cos omega t is minus cos, sin omega t is minus cos omega t. Okay. then you put the limit. So you know it is minus Vm by pi, because this minus we take it. Now you know upper limit minus lower limit means cos pi means 180 degree minus lower limit. You know cos 0 is 1, 180 is minus 1. So this is minus 1, the minus 1, minus 2, 1, minus 2, minus 2 into minus Vm by pi. So it comes 2 Vm by pi. Okay. This is the average value of AC, sinusoidal voltage. If it is different wave, then different value. Okay. Please. This is your average value of AC, sinusoidal wave. Maybe if your waveform is like this kind of square wave.
So this is for full load or half load, sir?
Not here full load, half load.
No, the full rectifier or half rectifier, I want to say.
Yeah, in rectifier it is different. It is full wave, because in full wave we get a 2 pulse output. Okay. You know, if we calculate the output voltage here, output voltage of rectifier. So this is your input. We coming on that. This is the input voltage, supply voltage is AC. But when we get a here output, we get a in single phase we get only 1 pulse in a 1 cycle. Only this in time period T means 2 pi. How much only we get a 1 pulse, but in full wave you get a 2 pulse. This also. So for full wave it is double. For half wave, in half wave rectifier, if we take a half wave rectifier, what is the average value? Vm by pi only. But in full wave it is double. Okay. We come on that. Okay. Okay. So first it is this waveform S. It is not a rectified output. Here we talk about the
एवरेज वैल्यू के इक्वेशन में एक्सप्रेशन में टाइम पीरियड विल बी 2 t/2 राइट
time period is T means it is a 2 pi, because actually if we calculate the average up to here to here, यहाँ पर भी actually हमने summation भी the summation also we carried out up to here, but
राइट सर तो हम लोग हाफ वेव का ही लेते हैं
yeah,
2 एंड डबल करते हैं उसका तो हाफ वेव का टाइम पीरियड विल बी t/2 व्हिच इज पाई
T/2.
So for half cycle we take a T/2.
Yes,
That
half
means-
cycle is T/2. But here because we are calculating for one complete cycle, that's why it is T means 2 pi.
then why are we multiplying by 2
Here it is the magnitude is multiple.
सर वी आर मल्टीप्लाइंग बिकॉज़ वी आर टेकिंग फॉर हाफ वेव अगर हाफ वेव के लिए ले रहे तो
Multiplying for
मल्टीप्लाई
magnitude. We multiplying for magnitude for because we calculate half wave, then it is double, then it give you 2 half cycle value. And time total time is given, na. Otherwise, if you take a T/2, then you again separate you multiple with time period also. Okay. If you calculate only this, na, means here is you put a pi only. If you like you want to only here T/2 integration 0 to pi, then if you multiple here, this is not give the correct value. Here you also multiple the time. Time is multiple, this also. So better you take a time is total is given T. Okay. Only for magnitude you have to multiple.
ओके सर
this will give the average value. Now you come, next value is RMS value. Actually, it is called effective because you know the voltage rating you mention on the nameplate of transformer, motors, lamp, bulb like 220 volt, 230 volt, 415 volt. These are RMS value. And your analog meters only measure the RMS value. Why it is effective? Means it is the value of AC, voltage or current, which produce the same heating effect like produced by the value of AC, value of DC, voltage or current. Okay, means we compare the heating effect. So value of AC which produce the same heating effect produced by DC. Okay, that is called effective value, and this RMS value is effective value. Okay. So again here square mean. So here is also we calculate the mean value. Mean means average. So again you have to calculate 0 to pi, then V d omega t. Average it is 1 by t. So this is the average value. Okay. Then square. So actually you do the square, V square. Okay. Like square, then mean. Mean means average. And total is into 2 for total average value. Mean. Double of this. 1 by, I have to use separately write it. 1 by t and 2 into 1 by t, double of this. Then square, then root. So see, we have to calculate square, then mean, then root. That's why it is RMS value. Okay, like suppose RMS value of AC is this. Very simple. Square means here we put a VM square sine square omega t and d omega t 0 to pi 1 by 2 pi into 2 and root of this. Please. Okay, here this go outside now, it is Vm by 2 to cancel by pi. Again this 2 to cancel, then Vm square by pi, this is constant, and then sine square omega t change. Okay, some formulas there, 1 2 cos omega t, like this, sine square theta equals to, we put this value here and integrate, then put the integration of sine omega t d omega t. Okay, so first we use a trigonometric conversion of formula, then we integrate from 0 to pi, then put the limits. Finally, you get a which answer? Vm by root 2. Please remember, for AC sinusoidal voltage, what is the RMS value? Vrms. For sinusoidal voltage, Vm by root 2. From this, we can calculate peak value equals to root 2 Vrms. If you know the RMS value, they can ask the peak value. Okay. Now again, in case of, as I told, rectifier. The rectifier output voltage is also pulse. That is not a pure DC. It has a pulse. So they have a average value also. They have a RMS value, means AC value. Always please, average is referred as a DC value, RMS value always referred as a AC value. Please, AC value or RMS value. AC value means RMS value, DC value means average value. Then two factors are there, form factor and form factor and peak factor, form factor, you know. Always please remember for this sinusoidal waveform, form factor and peak factor. Peak factor is peak value, means maximum value, by peak factor equals to peak value by RMS value, please answer. VRMS, VM by VRMS. Form factor is RMS value by average. Like here in AC case, what is the RMS value? VRMS is VM by root 2 and average value is VM by 2 VM by pi, correct? No? Average value. Now, if you solve this VM cancelled out, correct? No? Then we can say 1 by root 2 if we take in multiplication by 2. So it comes pi by 2 root 2. Please check this. 3.14 1.11. This is the form factor for sinusoidal voltage AC waveform. Okay. Yes, please, audible.
Yes, sir.
Now peak factor. So it is VM and your RMS value is VM by root 2. By there, this is cancelled. It comes root 2. Then it is, what is the value of root 2? 1.414. Okay, 1.414 is the peak factor. Please you remember this value, yeah? Peak factor and form factor. Here this VM cancel and it is root 2 only. Here VM cancel, then pi by 2 root 2. Now come to this numerical part. A moving coil emitter, thermal emitter, and rectifier. And the rectifier is connected in series with a resistor across 110 volt sinusoidal AC source. So this one turn, either it not written, then please you consider it is RMS, always RMS values. Okay. So he said that there is a one resistor, load resistor. This and suppose it is A1 emitter, this is A2 emitter. It is connected in series and a diode, PMMC type. Then it is thermal type. Then and the rectifier. This is diode. Now here sinusoidal voltage. One 10 volt. Okay, here. So when if this voltage is applied, when is the current is flow, then your diode is forward biased. Now circuit has a resistance of 50 ohm. This is the is 50 ohm. To current in one direction, total resistance of circuit. Not only load resistance, this entire circuit. And the infinite resistance in reverse direction, because when the reverse they see in AC, see, there is a when in AC input means there is a positive cycle, negative cycle. So when positive cycle comes, this diode is forward bias, positive, negative, like this. Then it conduct. Because only 50 ohm resistance, total circuit resistance is 50 ohm. Not only load. So there is a one load resistance, and suppose we take a ideal emitter ideal and diode is ideal, then this load resistance. But when negative pulse come, there is a reverse, it has a infinite resistance because diode has in reverse bias, it not conduct. So it has a total circuit has a infinite resistance, means no current is flow in reverse direction, only this direction the current is flow. From here to here, okay. Now, my dear, A1 is PMMC, permanent magnet moving coil type. A2 is A1 is PMMC type, A2 is thermal type. It work on electromagnetic and your I square RT Joule heating principle, okay? Thermal type. You know, thermal in AC, what is the heating I square RT value is RMS value, okay? So means A2 is measure, you can write in short, A1 will work only DC. So A1 emitter measure works on DC only, no AC. DC value of current. And A2 is thermal type, it measure This is not a DC value. It measure the second is thermal type. No? It measure RMS value. DC value means average value. Please, you now we calculate a current flowing through this circuit. So suppose when positive current is flow through the circuit. Okay. Okay. How we calculate? First we calculate a peak value. Peak value of supply voltage or applied voltage. Root 2 V RMS. It will give VM, peak value, okay, or maximum value. We get a 15556 volts. Then from this peak value, we can calculate the peak current. Here this supply current equals to load current, okay, in circuit here. Okay, here. Now we can calculate peak value of current supply current. It is peak value means of current, there is a peak value of voltage divided by total circuit resistance. Total resistance. Total circuit resistance during forward, okay? It is 50. So this is 155.56 divided by 50. What is the current? That is called IM, peak value of current. .11. .11. Now, please. Now we can calculate the average value. Please remember, for half wave, it is a half wave rectifier. For half wave rectifier, I average, I peak or maximum values, and then average value and RMS. For half wave average is, what is the average value? Only the IM by pi. Okay, not 2 pi. IM by pi. This is RMS value is what is the RMS value? Half wave for half wave rectifier. for half wave rectifier. The average value is this and RMS AC value. Please remember that is IM by average value. No, it is IM root 2. It is IM by 2, not root 2. Okay. IM by 2 only, average value. Now we calculate these values. What is the average value? This were IM we have calculated now. IM 3.11. Then this is the 3.5. What is the value? Divide by 3.11 divided by 3.14. 0.99. And this is IM is 3.11 divided by 2. 1.555. This is the values. Now he asked average value or AC value. Okay. My dear, your emitter is read the DC value. This is called IDC also. This is called IAC. So you know it work on both AC and DC. Okay. A2. Reading on emitter. So your emitter 1. Hello. Reading on emitter. First part. Second is reading on emitter. Reading on emitter. A1 read. This is because it is suitable for DC only. Because it is permanent PMMC type instrument, that is this measure only DC. DC average value. And this measure the A2 is thermal type, it measure the RMS value. You know what is the reading of A1? So this your RMS value is this average. Yeah. So this A1 read the 0.99 ampere and this read 1.5. Okay. Next is form and peak factor of current. So this is your current waveform, the calculate. What is the form factor? This form factor means again same. Your this form factor RMS by average. RMS by what is the RMS value? 1.555. Average value. RMS by average. RMS by average. And this is VM by VRSV. It comes 0.77. No, it is not ampere, it is factor. Huh? ये क्या यार? इधर क्यों बता दिया? 0.99 ना by average value. So you divide it 1.555 divided by 0.2. It is 1.5, sorry, 57. Then peak factor is peak value by average or RMS. Peak by RMS value. Okay. Peak by RMS. So this here peak value is, please put it, this value is not for AC, RMS and peak. Okay. Correct. So this is what is the peak value here? IM, that is 3.11 divided by RMS value is, here it comes 1.555. Okay. This factor we already calculated. Okay. Comes to okay, dear. So this is the form factor and peak factor. Now one important thing, when we talk about half wave, diode half wave rectifier, this is full wave. Full wave rectifier means with the two diode or four diode. Four diodes. Two diodes and four. Here it is only single diode. In a half wave rectifier with single diode. So here, if we calculate na there, please. Peak value in both na same peak value. Because if we neglect the drop, then peak value of voltage are here same. Okay. Then if we calculate their average value, V average means it is a DC value actually. That is VDC equals to, for half wave it is average value means Vm by pi, but for two diode it is 2 Vm by pi. Please. Then if we calculate AC value means RMS. That is AC. AC value means in AC we define with RMS value. That's why it is AC value. So here, if we calculate AC RMS value for half weight is Vm by 2, not root 2. Generally for sinusoidal it is Vm by root 2. So here for full weight is Vm by root 2, but here it is Vm by 2. This is AC. If current also, if you give a current, then it is Im by pi, average value of current. It is Im by 2, like this. Here it is for current also. Here if we also calculate, now here it is Im, current peak value. Current here, this is current Im, this is 2 Im by pi, this is Vm by root 2. Here it is current, for current also it is same. Yeah, please. This is the AC. Why we, this is for output, not AC. Actually, if you draw here diagram in the rectifier, what we show? This is your rectifier supply voltage input side. Here see, in half wave diode, this is your half cycle we get only positive cycle when positive pulse. This is your output voltage. This is your, here we show the output. Here we show the input source voltage, supply voltage. Now my dear, this is not a pure DC. This, it is a pulse. That's why it also has a peak value. This is your output voltage. This also has a peak value. Okay, peak value. We can calculate the average value of also this, the average value. And here RMS value also we can calculate. That is called V RMS. It gives you AC. So for this also we can define these values. Actually we are calculating for output, but these are also peak value, average value, RMS value. Okay. Same for current. You know, this is V. Now you know V equals to, actually it is load current, output current into load resistance. Across load we measure this. Or if it is VDC, output DC voltage means average value. This is called average value. This color. So it is DC. Sorry, not AC. Here DC means average value. So how we calculate average value? If you know the DC current, average value of current, then RL. Okay, so VDC equals to IDC into RL. This will give the average value. This is your peak value. This is the peak value of output voltage. This is peak value of output voltage. Again, it is same sometime. It is a VM. It is same like this. If there is a no drop, this is the VM. Now average value. Same like here we can calculate the current waveform. So if voltage is current is also same like this. Okay. So here is also current like it is a IM current, IM. Then here average value of current IDC. Then IRMS also we can calculate. That is called IAC. This average value. If we calculate here average value means it is IDC. Average value is DC value. Okay. RMS value is AC value. Please. Okay, dear. Now, if we do this, suppose it is a full wave, means in this also we get a rectification. Now, if it is become full, then my dear, this average value will be double. Because earlier in this here to here we get a one cycle, but now it is double. Okay. That's why this is the difference in single and full wave. Got it? Explain the application of PN junction diode in the rectifier electronic circuit. Lot of application of PN junction diode in rectifiers. In rectification, we use a diode. Now the numerical. In a full wave rectifier without filter, the load resistance is this much kg. Each diode has a, so it means has a forward resistance is this much kilo. If peak value voltage is applied to diode, to each diode, is this peak value of voltage is given at this much. Calculate. So here we consider this is a full wave with two diode. Okay. So please you draw the circuit. In diode or full wave rectifier. This is your transformer initially here. Then we have this side. Here, there is a center tapped secondary we use. Then this diode D1. Here, diode D2. It is D1, it is D2. Without filter, this is your center tapped secondary. This is your load resistance. Oh. This is your RL. Across this load, we measure the output voltage. Okay, this is your output of rectifier. Now, my dear, it is given how much? 4,000 ohm. 4,000 ohm. This RL. 4,000 ohm. Because 4 kilo means 4,000 ohm. And this diode forward resistance, when it conduct, diode is conduct, then it offer a diode resistance is RD, 800 ohm. Okay. when total circuit, if now here means in input, okay, when positive cycle occurs, when positive cycle occurs, now this is positive, this is overall negative. Now here means this positive, this negative, this positive, this negative. So he said that across each diode, what is the voltage? Maximum peak value is given, Vm. This also. Supply voltage peak value, Vs. This supply voltage across each diode is how much it is? 120 volt. This is 120 volt. Peak value. This is a peak value. Okay. Then see, when the positive pulse comes, this diode will conduct. This current is flow. When the negative pulse comes, means this is negative. After this is negative, means now when during this pulse, this is become negative. I write here. This become negative, this positive, this negative, then again negative, this positive. It means this will conduct. Then current flow in this direction also. Okay, same here. Your supply means current and load current. This is load means output current here. So here always load current is flow through this. Okay, like from this point to this point, A to B. Suppose this is A to B. Yeah? Okay, unidirectional. Again in this, here, this is the way we'll get like full wave. So here diode D1 will conduct, here D2 will conduct, here D1, here D2, like this. Okay. Now we can calculate first of all, what is the peak value of output voltage? Output means load. So across load. Here first not load, it is supply voltage. Means supply voltage. It is peak value means Vm. It is how much it is given? 120 volt. Okay. Then we can calculate the therefore peak value of output current. Output current means load current. Load which is flowing the load. Output current means load current. That is peak value. So you know, if you draw this circuit, what is the supply voltage here? This much. Then total resistance, this diode resistance and this load resistance in come in series. So here you write diode resistance plus load resistance. Okay, dear. And you take a peak value, then we get a peak current. So it is 120 divided by 4000 plus 800. How much? What is the value we get here? This is the peak value of load. You know, load current equals to output current, because it is same current. Here supply current and here load current. Load means output. It is the peak value. Okay. Then please. Now you calculate, if you get a peak value, now average value you can calculate. This will give you peak value is 120 divided by 4,800. It comes 0.025 ampere. Now what is the, first of all, what you ask, please? The average value of current. Now it is a peak value. Now we calculate average value. Therefore, average value of load current, or it is average value. Na? So I average means DC. It is represented by DC. Yeah? So you know average value for full wave is 2Im by pi. 2 into 0.025 divided by 3.14. Already into 2 divided by 3.14. It comes right here 0.0159 ampere. Okay. First part of this question is solved. First part. Then next what he asked? Efficiency. Very good. Now we ask the efficiency. Yeah? Second, efficiency. So you know efficiency always output by input. So here DC output power. When you know efficiency is DC, we get output as a DC. So you get a output DC power divided by input AC power. Input, so you have to AC input power into 100. Please. Now actually they should be in same unit, na? Okay. So either always na RMS value. Please, what is the power? Total power na? Always we take RMS values of AC. In DC, you know output. What is the output current, output voltage? You know na? Then we can calculate a power. Okay. Hello. So now this we can write na power DC power by AC power input into 100, correct? Now my dear, DC means your DC output voltage, average value we take, okay? VDC, IDC, okay? Or either you from I square na IDC square by RL. L means load resistance only you take. Either you by this or by this you can calculate. Okay. Any doubt, please? या तो ये फॉर्मूला लगा सकते हैं आउटपुट पावर ना इन DC I square RL or either this voltage into current. So let us with the voltage into current we can calculate, or either you calculate by this. This is also same. So now actually current we know, DC current we calculate na IDC. Now we want voltage. So VDC we calculate. VDC equals to IDC into RL. Correct? Load resistance. Okay. Here, if you current you know, average current, then this low voltage we can calculate. Average. My dear, this current is average current and it's 0.01592 into RL is load is 4000. My dear, this into 4000 if you do na, you get a 69 watt, okay? Sorry, it is voltage, first it get a voltage, okay? This much voltage, Now we can calculate, hello? This is 63.694 into the current is again you multiply by 0.1592. So it comes, you multiple with it comes 1.014 watt. Okay, now AC input. So for AC, please you take a RMS values. Please remember, always RMS value. What is the AC power? You know, apparent power we take in AC power. So you take a, it is a product of RMS voltage into RMS current. Please remember AC input, okay? So this, what is the average value, RMS value of? So peak value of voltage is given. Hello? Supply side voltage, na? Please. What is the, V peak, VM is given 120. Then VRMS will be. Now please, it is a supply side. Here you not apply the rectifier formula. Actually, now we calculate the RMS value here before the diode, here in supply and this side, okay, here before this diode, okay. So it is a sinusoidal voltage. Then what is the average value? VM by RMS value, VM by √2. So it is 120 by √2. And current RMS. Actually, current is output current equals to input current, Hello? The same current here to here is the same current, Correct, This current is same current is flow here to here. The input means RMS value of load current is itself the RMS value of supply current, correct, So already we calculate the, peak value, of this current. Now RMS value we also calculate. What is the IRMS? For full wave, it is Im by √2. So it is Im is 0.025 divided by √2. What is the value? Six ampere RMS value. Now here, so this is the same, 0.0176 ampere, and this voltage is 120 divided by √2. It come 84.85 volt. Now if we put here values, RMS 84.85 into 0.0176. $1.493 watt. No, now both power, then you just put here. Hello. What is your output DC power is? Output DC power is this. It is 1.014. AC input is 1.493. Okay, so it comes 67.89%. Any doubt, please? Input power and output power you calculate, means in across load, your after diode and before diode you calculate the power. And you know output is DC, that's why voltage into current DC values. Okay, average values. And before AC, it is AC voltage. Before diode, it is AC. Then you calculate RMS value. Okay. Next, he is asked the regulation when load current is 10 ampere. Now, please, he is not considered this load current. He given in third question. He said that regulation is load current of load current means always DC value. So here it is given if IL load current means your output current, that is DC value. Output load current milliampere. Milliampere means 0.010 ampere. If load current is given, if you write load current means output current DC value this. Then he asked the regulation. So it is percentage voltage regulation. So in transformer, motor, in transformer and alternator we calculate no voltage regulation. What is the voltage regulation? Here. This is also across the load. If one circuit we make here again, suppose this is the supply voltage here, then diode. Then you know here we put a one resistance. This is your load resistance. Across this load resistance we measure the voltage. Okay, this is your RL. So now here this is your supply voltage. Okay, so after diode. Now he said that if we remove this, now what is the open terminal voltage? If we remove this load, then open terminal voltage across this load. Across this load we measure the voltage, output voltage. Okay. So see, open circuit voltage and no load. What is the regulation formula? As transformer and motor, same, no? Hello? No load. Regulation means, see, V output voltage, VDC, VDC means average output voltage at no load, minus VDC at load, full load, rated. Divide with respect to full load, we calculate this P2. DC output voltage. So my dear, if this load resistance is not there, then you know there is no drop in the diode. No drop in diode means this output voltage at no load. Please write here at no load means DC, this output voltage, VDC at no load equals to here, that is the your, you know, the here this voltage is there. If suppose VM, the same value we get here, then you calculate their RMS value. Okay. So what is the voltage at no load? It is the you know VM. Now we calculate the DC value, means average value of this. So what is the average value? 4. Now it is not a single. For a full wave, then you take a 2 Vm by pi average value. Okay, and here Vm is 120 we take. 2 into 120 divided by 5 means 3.14. So at no load VDC. This, okay. What is the value it comes? It comes 76.43 volts. Now at full load, when there is a full load, means this resistance is connected, then there is a drop also in this after you get a here. Now you calculate VDC. Now we can calculate IDC into RL, means across this load resistance. This is your output voltage. Across the load, we measure this, then it will give you IDC if this load current is flow. If we calculate a current through this resistance, then what is the this? So this is at load. You calculate by this. So you already know the current. Now DC current is given, my dear. Please you not take this. You take this. It is given 0.010. RL is 4000. It comes 40 volts. So see why this difference. At no load, no drop across the diode generally. At no load, why this output terminal is high? Because no drop in the diode resistance during conduction. Because diode resistance is also 800 ohm. But at full load, the current is low, there is a drop, then we get a reduced voltage. Okay. The input average value is output we get at no load, but here it is 40. Therefore, this voltage regulation we calculate, this is comes 760.43 minus
91.07.
yeah, good. 19.99. इधर कितना आता है? सॉरी,
91.07 है.
40. 91. Okay, this is the draw. Okay. Mostly half रहे हैं. Okay. It is 90% voltage. Okay. So, see, this is the term, efficiency and this regulation. This was the two numerical which was asked in your this. So here we take a break, we take a 10 minutes break here, so 15 minutes like now 3:35 now. So we have taken 3:40, 50 we can start.
Okay.
Yeah. Please do not leave the meeting. I will put in mute.
Okay.
Hello, audible?
Yes, sir.
Here, if you see, this is the August month question paper. Explain the meaning of the terms power factor correction. As I told you, correction means improvement. If we improve the power factor from low power factor to high, what is the advantage? It is recently covered in power factor. We yesterday, I think. Your load current is reduced, voltage drop is reduced in the circuit, losses are reduced because voltage drop, then load current is increased. Then losses, I square R losses will be high. Efficiency is improved. Your electricity bill is reduced. Adverse effect. Correct. And your load on the transformer or alternator is reduced at high power factor. That's why we improve the power factor. Correct. Explain with the layer of diagram. Low power factor correction will be affected in three-phase circuit. You have to draw the three-phase diagram, show the loads and power factor, how we improved by the static capacitor. Then other method by synchronous condenser. Overexcited synchronous motor, we operate parallel with load, correct? Or either automatic voltage. Automatic power factor correction we are used. Okay, so question 1 is correct. Then second is, electric motor, so your three-phase squirrel cage in induction motor have a low power, low starting torque. Then how we improve the starting torque? By changing the rotor construction type. So instead of squirrel cage, we use a double cage rotor or wound rotor. Okay. Any question about this? Hello, doubt in wound rotor and double cage rotor?
The second वाला थोड़ा सा explain कर दीजिए.
Actually, in second, it is a squirrel cage rotor only, but we use a double cage, inner and outer cage. There is a different type of bar is insert, thin or thick. Okay. So here, this is your, rotor surface. Okay. So here on this, we make a slot. Then there is this is like outer. Here is also inner cage. It is a large. This is the shaft. So this entire periphery has this kind of slots. So here we put this type of bar here, but large size cross section area. Okay. So when this rotor is rotated, no, not in first rotate. First, no, there is a flux is there in the air gap. Resultant. It linked with this. Now these rotors are short circuit. Now current is flow. So there is a current in inner cage and outer cage. Correct? There is a current in both conductor are there. So actually there is a two circuit here in the rotor. Rotor circuit, equivalent circuit is rotor circuit we talk about. There is a rotor and reactance. So in double cage, I will show you. Just a minute. There is another deep bar rotor is also there. Actually, we see now there is a two circuits like parallel. Inner and this. Inner outer cage now. Okay, we can draw like this now. Here there is a two circuit, okay, for your rotor. This is your rotor EMF, like they are act as a parallel. So suppose this is outer cage resistance R2, it is outer cage reactance. Slip times it is also there. Same like it is inner cage, it is outer cage. Reactance in both are inner cage. Means inside rotor, okay? Okay, now this rotor current is in total here. Major part is from outer cage and inner cage. Okay, this rotor current IO. Here it is rotor induced voltage low applied. Correct. So total part of rotor current it is divided in two paths, inner and outer cage. Actually, now cross section area is less means this resistance of outer cage. This is outer. This is inner. Inner. Actually, resistance is always fixed. So generally, it has a high resistance, which outer cage because it is a thin wire. R equals to rho L by A. If A is so, this resistance is high. So this is high, this is low, correct? Now impedance is changed with now at starting, at starting. when speed is 0, slip is 1 maximum. It means because they are slip times also, na, reactance. Okay. So slip is 1 means your this reactance. My dear, now if suppose there is a two conductor, like suppose parallel, they are like this. Now current is here, I1, this is I2. So magnetic flux due to this conductor is encircle this only. This. But outer conductor current is encircle this complete. Which has a more flux linking, more flux linked with outer or inner cage. The flux produced by this only, it circle this here. This circle, but this only this much. Now maximum flux linked with inner or outer cage?
Inner.
Inner, yes, great. So means at starting, when slip is 1, this reactance is, it is high. This is low. So overall your current, maximum current is, rotor current is passed because impedance. If we talk about now, we will come to the impedance, inner cage and outer cage. Inner cage impedance at starting is high, correct? Due to this. And this resistance is low, this reactance is low because less flux is linked, it is high, then overall it is high because resistance is less part. This is low. So my dear, in starting, it is a high resistance. This is high resistance, but maximum current is passed, starting current passed from outer cage. At starting, maximum current is passed from, at starting, maximum current is passed from outer cage. Because impedance at starting, this impedance is low. That's why maximum current is passed from outer cage. This current is high at starting. Okay. Because current is always take a low impedance path. Okay. So at starting, see, resistance is high, but overall impedance is low. Okay. That's why maximum current is passed from outer cage. That is of low cross-section area, means resistance is high. And now if rotor resistance is high, then torque is high. Correct, na? Torque is proportional to, rotor resistance. Correct, na? Okay, because this is K1 slip E2 square R2 by R2 square plus XX2 whole square. This is the torque, na? So it is, if resistance is high, therefore, slip ring induction motor has a high starting torque because we add the resistance in, it has a high resistance, correct? So same like here. So please, at starting, maximum current is passed, you just remember, maximum current at starting pass from, flow in the outer cage. Okay, now you please check under running condition. When motor running with, now slip is, slip is 4%, full load slip. Now when slip is come in picture, my dear, this, slip times of reactance. So suppose this is 10 ohm, this is 20 ohm. Now it is multiple with slip. Then impedance is reduced. because reactance is reduced due to slip. My dear, now you know. Now, this due to this change in reactance, resistance is fixed. Now there is a change in impedance. Now, inner due to low resistance now. Okay. Earlier there is a low flux linked with at starting low flux linked with outer cage. That's why impedance is low. Now due to slip this impedance is changed. This become low. Okay. Now which has a higher? Because inner cage, this I2. Inner cage has this flux, but due to slip it's changed. Hello. Now running condition actually this flux, this impedance are reduced. Impedance are negligible. Okay, this impedance is. Now current is select as per this resistance only. Okay. Correct. Actually at starting slip is 1, then this reactance actual value. Correct. Now reactants are negligible because it is both are multiple with slip. Okay. Now which circuit has a high impedance? Those have a high resistance. So now earlier this has a low impedance. Now running condition this has a high impedance. Now outer impedance is high because resistance is high. Then now current is shift from outer cage to inner cage under running condition. So actually in double cage what happened? There is a 2 circuit, means in rotor 2 bars. So this current is changed. Okay, it changes the circuit path. Okay, at starting it is from outer cage, maximum current pass from outer cage which has a high resistance. Just you in simple word you write outer cage, inner cage. Outer cage has a low cross section area, inner cage has a large cross section area. But at starting high impedance is offered by inner cage. So current is flow through outer cage which has a high resistance. So high resistance means high starting torque and high resistance means high power factor. See, there is a 2 parameter you remember, rotor current, rotor circuit power factor. Okay, this is 2 parameter. So see, this is your E2 by Z2 like this. So it is, if impedance is high, the current is low. So we write a low starting. Power factor is R2 by Z2. So if resistance is high, power factor is high. This means rotor current is low. So high power factor and high starting current. High torque. Torque, please. So starting torque. Power factor, because you are torque, just you understand by this also. High resistance here. It means power factor is high, then your torque is directly proportional to, I2 cos phi 2 and phi, this plug. So if you remember this power factor only, then you can also reply. High power factor, this outer circuit has a high power factor. Okay. Because resistance is high. Okay. At starting we have high. But in running condition, current is shift here. Okay. It take a inner path. Now inner path has a high resistance. Low resistance. Correct. So losses is reduced in under running condition. So means your motor give the both performance, like there is a motor under starting condition and running condition. Both things are improved. See, under starting, torque is increased, power factor is increased. Under running condition, dosage also reduced because rotor resistance is reduced. It take a low resistance path. And starting when selection is due to overall impedance. So overall impedance are changed. Okay. Running condition which has a low resistance. And out in starting high resistance, but impedance, overall impedance is low. Okay, dear. Now I think you understand. Got it? Hello?
Yes, sir. Yes.
Correct now? Same like a deep bar rotor also. In some cases, only single bar, but it is a large bar like this. This kind of same concept. It is also work on the skin effect. If a large conductor like this, so due to skin effect, the current is under deep bar rotor is also there. In deep bar rotor means deep size of bar we put like this, not like this, here like this. So at starting, or you write this way at starting. At starting, rotor slip equals to slip times of supply frequency. Slip is 1 means at starting rotor frequency. This you can write. Under at starting, your speed is 0, slip is 1, then rotor frequency is equals to supply frequency like 50 Hz. So if frequency, then reactance, reactance is high because XL equals to omega L equals to 2 pi FL, correct? But under running condition, the motor running kar rahi hai with slip 4%, then your frequency of rotor is 2 Hz only because 0.04, it is 0.04 into 50, so you get a 2 Hz only. If frequency reduced means reactance is reduced, the rotor circuit reactance is reduced. Okay, so this is the due to skin effect. It take in rotor the effective cross section area is reduced. Okay. Due to skin effect, resistance is increased. So at starting, rotor frequency is high, then skin effect is high means resistance is high. Then it produces a high starting torque. But when running condition, the frequency is reduced, skin effect reduced, the road resistance is reduced, means impedance. Got it? The deep bar rotor is also work in that case. Okay. Same like here happening. Frequency change at starting. Okay, so there is a impedance come, but high impedance of outer because more flux is linked. Frequency in both cases are same, but due to flux linking, the impedance is changed. Okay. Now, okay, this is the wound rotor and double cage rotor. Soft starter, So in August month, actually, in paper section 1, all 3 questions you can write easily. Advantage, disadvantage of soft starter. Where you compare with star delta. In star delta, there is a voltage is suddenly change. It is multiplied by √3. Then motor get a jerk. Second, transition. Even if you do automatic your star delta starter also, there is a contact moving time. During that period, the motor does not get a voltage. Due to inertia, it rotates, but there is a voltage is gone. It is cut off, then it is multiplied by √3 times. Okay, but in soft starter, it will gradually increase the voltage. And this soft starter also used to speed control also. Star delta we cannot use. You know, this soft starter we can use for speed control. How? You reduce the voltage by controlling the firing angle. Then your motor speed is controlled. Okay. But with star delta, we cannot control the speed. Correct, na? Got it? Hello? You know this star delta starter and this soft starter, please. Hello? Audible?
Yes,
Yes,
sir.
sir.
Are you aware or not? In star delta, this starter either diol or star delta. When we compare the soft starter with conventional starter, what is the conventional? Diol or star delta? Correct, no?
Yes, sir.
So you know they are only starter. They reduce the starting current. In star, actually, diol starter not reduce the starting current also. Correct? Only protect the motor from overload short circuit. Here rated voltage is applied. That's why in dual starter there is a 8 and 7 times, 6 to 8 times current is high. Huh? Now if we talk about the star delta starter, it by reduce the configuration connection, the voltage is multiplied by √3 times. During starting, it connect the motor in star, then it convert into delta. Okay, so here, okay, it reduce the current, but there is a transition period and there is a double cable is also required, double run in star delta. You know, suppose this is your panel, star delta panel, star delta starter panel. Then here too, this is your motor. It is some different location, either 10 meter, 20 meter. My dear, to connect this, it required 2 run of cable. Are you know? 2 into 3 core. Two into 3 core, okay? 2 run. Why? Because the terminal we extend this motor, there is a 6 terminal, we brought to this starter, and here is we use a contactor to convert the star delta. But you know, this is the disadvantage of star delta, my dear, another. But in, you know, in VFD or if you use a soft starter, only single run cable is required. 1 into 3 core only. Okay. Got it?
Sir,
In
can you
VFD,
explain one more?
yeah.
Can you explain once more the two-run cable?
Tell me, what are you asking? Why we require 2 run cable? Hello?
Yes, sir.
Yes, that is I am explaining now how, you know, how we convert, change the connection. You not, I think you not seen the star delta starter practically. How you connect the star delta starter in motor star delta starter? See, this is your motor. At their terminal block, there is a 6 terminals come. Correct, no? Or we show with the winding. There is a 3, you know, 3 windings are there in motor. now to to connect in star or delta, this all terminal we have to brought, this all 6 terminal we have to brought to your star delta starter here. Then we use here contactor, 3 contactors are there in star delta, main, star and delta, correct? So this one core, this is one run, this is second run of cable. Okay, अभी आप अगर देखना practically, if there is a one motor is connected to star delta starter, there is a 2 cables will be there. Okay. Understand?
Yes, sir.
Yeah. Now in VFD and DOL starter and soft starter, only single run cable is there. So this is the disadvantage also. No, you have a cable cost is come, installation is termination. Okay. And they not when we start motor, the purpose is of starter is over. It protect from overload short circuit. Okay. But if you want to change the speed here, then it is not able by star delta or DOL starter. In VFD or soft starter we can use. Okay. Correct. Any other? If you have any doubt, please.
सर एक बार ऑसिलेटर और रेक्टिफायर और उसका सर्किट आया था सर, उसका बता दीजिए.
Oscillator circuit. Okay. This is the software starter here discussed. This is back-to-back connected, this diode we use. Then we can advantage of soft starter. Please improve efficiency because losses are reduced here. Efficiency of soft starter using solid state device is more. Controlled startup. Current can be controlled smoothly. Alternating the starting voltage, ensure the smooth starting of motor, no jerk. Control acceleration of the motor also smoothly. Low cost, and you write the advantage of speed control will be also possible. Okay, during running condition. Disadvantage, because soft starter is solid state device, they fail. They not repair. Correct? They are replaced, no? Only. And it is a high costly also. Correct? Next is this reverse power relay, these things you have to learn, please. No, the rectifier circuit, so you can draw na half wave, full wave rectifier, not an issue. Only oscillator and what other is amplifier. So this circuit you can draw rectifier, half wave, full wave. Then next is I will show you the PN junction diode if they ask. Then American oscillator. This is the power factor, how we improve. This is the load, this bank we connect, okay? Star or delta configuration, then power factor is improved. Yeah, this is the your diode and ceramic starter. Yes. So rectifier, okay. Amplifier. Hello. For amplifier, you know, we use a NPN or PNP transistors. Okay. Hello. First of all, your rectifier circuit. Rectifier we use either diode or SCR, correct? First is rectifier circuit. Then he is asked amplifier. Please note down. Fire circuit. Then third is oscillation. Oscillator circuit. In rectifier, we use what is the device? Name device which is used to make a diode or SCR thyristor we use. In amplifier we use a transistor. Tors, okay? Transistor like PNP or NPN. NPN we are generally use. In oscillator, tank circuit actually they are. Hello, oscillators are generally op-amp we use. Oscillator is an electronic device that produces the period oscillator gain. A sine wave or square wave oscillator convert into DC from a supply to an alternating current. So it actually gives the constant signal, then it convert into oscillate it. Commonly electronic device generated radio, TV, there is transmitters, clock signal, regulator, computer. We use this now.
So capacitor, inductor, right?
No capacitor. Yeah, capacitor, inductor, oscillatory circuit are there. That is called RF circuit. Sorry, radio frequency. But often we use, operational amplifier. Audio range. There is a audio oscillator RF is produced the radio frequency. Okay, so you please let here I draw. You can draw the circuit. Rectifiers are either a half wave, full wave rectifier circuit you can draw. Simple. This with device, then circuit. Okay. Here circuit you draw. Here, half wave rectifier. This is your input this isolation transformer. Then this is diode. So we are showing the single phase diode half wave diode rectifier. Diode rectifier with RL load. So here you show the load RL. Across this we get a output voltage, okay, V output. This is your diode. Then full wave also. Then with the double diode you can show, or by the bridge rectifier. Okay, dear. This is your diode with the full wave with the two diode. So this is your load resistance. So it is full wave. Okay, these things are okay. Bridge rectifier you can also draw. Now in here we use with the transistor we can draw the amplifier circuit. Okay. So generally we use a NPN. Okay. It also amplifies the signal. Here amplifier means. First you draw the transistor. This is the symbol of transistor. Okay. There is a biasing resistance, here. Now if suppose it is PNP, means now it is negative, highly doping. So the current is flow from negative to always positive to negative. Current is flow, right, in battery life. So here it is N, P, N. So here current is exit, okay, from P type to N type. So this is, collector, base, emitter. Now this is the base. Okay. Now here we coupling capacitor and this biasing resistance. This is the base resistance because it is connected to base. Okay, this is a base. This is collector. This is emitter. Emitter, base, collector. Sorry, collector, base. So here base resistance, and here we apply the collector voltage VCC. This is your load resistance. Across this we get the signal is generated. Okay, and it is ground. This emitter we gave to ground this. Got it? Okay, here we apply, this is VCC, applied signal. This is coupling capacitor. Please, coupling capacitor, these are biasing resistance and load resistance. Across this we measure the output. So here input. Here if you know, the input is, if you show na, input is this much here. Input. Now it amplify this. This is the input, plus minus this. Okay. Now we get a high output. It is enlarge. Amplify means. Okay, it is VCC. Here we get output plus minus. This is input. This is input. This is output. We get output. Output. Okay. Across load we get. Now oscillator. We use a op-amp. You know, in op-amp, operational amplifier. That operational amplifier is used as an oscillator. Okay. So here there is a 3-terminal. Positive, negative, and gate. Plus, sorry, this is positive, negative, plus, here minus plus. Here is also, there is a coupling capacitor. Here we apply the voltage. Now there is a resistance connect across the gate. Between gate and here is also. This is negative voltage. This is positive voltage. Okay. V plus. Okay. Then here is also resistance connected. Or. This is the resistance. Here another. This we do grounding. This is also. Okay. Often circuit is used to produce of the oscillations. Operational amplifier. Okay. Okay. Please take a screenshot. This here we take output. Okay. V output. Okay. Okay, so here we use a device is operational amplifier, op-amp. Here transistor, here diode or SCR. Okay, and these are the circuits. Please practice this. Next, part, please.
Sir, can you please explain reverse power trip once?
Which
Reverse power trip, sir.
reverse
Reverse power trip, sir.
okay, reverse power trip. Okay, yes. Power trip. Reverse power relay, actually it is basically induction disc type relay here. Here actually there is a induction disc type relay. If you draw, this is the U-shaped magnet. Correct. Here there is a center. This is the magnetic core. Now there is another magnet. This is called a shunt magnet core. Now there is two coils are there. Here we put a one coil that has a large number of turns. Okay, dear. This is called pressure coil or potential coil, and it is connected across the voltage, means across the supply, that is. And here there is a less turn, like this only, one single turn here. This like this. This is another set of terminals. Now this is actually current coil. This is called current coil. Okay. So there is a two coils are there here, current coil and this. This is CC, current coil. It is connected in series. Okay. So here actually the load current is passed here, and here due to potential difference current is flow. Okay. Let us here when current is passed through this coil, so there is a magnetic flux. Here is upward in core, this upward magnetic flux is there. Like this is due to this pressure coil. So let us, it is phi1. Due to this current, there is another flux is produced. Okay. So it is here another flux, phi2. Okay. So here in this coil, here in this ear gap, this is a ear gap. Here two flux are there, 1, 2. Now let us we mount here one disc. Here one disc is aluminum disc, paramagnetic metal disc is mounted here. It is free to rotate. Now this flux, this two magnetic flux develop a force on the disc, this aluminum disc, and it is coupled with a, this is connected with mechanic, like here flag contact, like, okay, this, they make a contact, here we think, this two contacts go to your trip coil. This go to trip coil circuit of your circuit breaker, and this is supply coming from CT, current transformer. This is coming from PT, potential transformer, if it is high voltage side. Otherwise 440, here it comes from PT terminal. Okay. Now actually, like in single phase motor, how the torque is developed in rotor? Due to there is a starting and running winding, there is a two magnetic flux in a single phase motor, correct? No? There is a two fields there, correct? Due to running main winding and auxiliary winding, correct? So there is a also same like here is a two flux, okay, phi 1, phi 2. You know, if there is a two flux here, there is a angle is alpha, then they develop a torque that is proportional to phi 1, phi 2 sine alpha, always, please. This is the torque equation. Always in, if there is a two magnetic field, due to their interaction, there is a torque is produced. This torque is work on this disc. And if suppose it is rotate here, anti-clockwise here like this, or in one direction, this aluminum disc, this is the disc. Now here suppose we put a one stopper, we will not rotate it. Always the force is there, but we stop it. Okay. Now I will show you here one feeder. Suppose this is your bus bar. This is your bus bar. Now there is a one feeder is coming either from alternator. Okay. So there is a circuit breaker. I will show you simple. This is your breaker. It is closed, suppose. This is your circuit breaker. And this is the feeder. Suppose there is a feeder, then here CT is also put here, CT. Then maybe suppose it is an alternator. It connects with this bus bar. Okay. So general case, what is the current is flow in this direction to from this alternator to this bus bar, because some load is there. This load is connected to this bus bar. Okay, so it carry the current to this. Okay. Now this is the circuit breaker, and there is a trip coil. In the trip coil, you know, there is a battery supply, auxiliary supply. Then there is a contactor. This is the contactor here, NC. For to make this is the contact of this two contacts here, or either this trip coil contacts here. These two terminals, this comes here. So they close this contacts. Okay. Either you saw like this. Okay. If we short this contacts with some arrangement, then this circuit is healthy. Then trip coil get a trip coil. It can close, then it push this plunger, it will open. Now how the action take place? See, now this is coming to this CT, okay? This is connected to this CT, okay, dear? And here some PT is there, suppose, there is a, supply is coming to this PT, okay? Okay, two wire, one is ground and some, okay? There is a PT terminal, okay? Now, my dear, current is always flow in this direction, then there is a force is on this side, on the disk, then it is protect. But now, suppose inverse current is flow. So you see, when this direction, the reflection in CT is in this direction, actually. Or either you take it like this way. Initially, suppose this is a feeder we take, not a machine, suppose. Suppose this is the feeder, some low feeder. Now current is always it downside. Then in CT, reflection is this side, okay, opposite. CT में opposite रहेगा, okay. Then the direction of current in CT, it is this side means this side, okay, this side. Okay, dear? Okay, and potential polarity is same. Potential polarity is not change. It means always current in this pressure coil is the same direction. So like in motor, how we reverse the direction of rotation? Only in one winding we change the polarity, either starter or auxiliary winding, starting winding or auxiliary, correct? So same here, when now suppose reverse current is flow, means suppose this is the current is flow this way in the feeder. Then CT, there is a, in induced EMF in CT is in different direction due to Lenz law. So it is now reverse. Then current in this coil is change polarity. Then this flux is change. My dear, now new flux is induced in downward direction. This, okay. Due to this, my dear, this phi 2 is become this direction, right? Okay. Now see, if this the direction of flux is reverse, means it is a vector, it has come this side. So if this angle is changed now. Hello, means this is direction is changed. Okay, so it earlier it is this side, now it is this side. Okay, let us this is phi 2, now it is new flux is this opposite direction. This is now this side. Okay, phi 2. So due to this alpha, now it is greater than 19, means it comes negative value. So this negative torque will come, correct enough? Due to this angle, now this torque is minus as this. So now reverse torque is produced, means this disc is rotated in opposite direction. Then it is, when it rotates, it close this trip contact. This. Then your circuit breaker will trip if reverse current is flow only. In one direction, no trip, because disc is stopped with a stopper. Got it? So if you know the operation of single phase motor, same like here in there. Okay? This is your reverse trip. Got it? Any doubt? Hello.
Clear, sir.
You know, in CT, the direction is changed, then your flux direction is changed, means torque is in opposite direction is produced. Your disc is close the trip contact, then your breaker is trip if reverse current is flow. Okay. Any other?
So why in PT the flux direction is not changed?
Because potential is the same, na? Voltage potential, bus bar polarity you are not changing. Bus bar polarity is same, na, always.
Yes, sir.
It is coming from the bus bar, okay, your feeder. Okay, this. This is your PT terminal, it is. Next. Okay, now this variation, I will share na this voltage profile. Okay, recovery. Now here numericals. This we have already solved na this. No. What is the frequency at half load? Correct. Now transformer. This numerical. Hello. What is the synchronous speed? Rotor when 4% slip. Rotor frequency when slip is this. Sorry, this is the rotary speed is 600 RPM. Okay. It is a wound for 4-pole. Then you calculate. Now large transformer, where they use in the power stations and in transmission and distribution. Okay. Efficiency range is 97 to 98%. 96, 97. Protective devices. And I have here the maintenance requirement also for dry type transformer. Okay. This is a very important question. It is, but no, it is simple. No, the alternative is different. Okay. Easy. Now these are your, you please prepare this also safety question. Next you come to your October, November, sorry, August, September month. September question paper. Yes, please. Have a look. So here, you know, this all three circuits, as I told, sketch a DC voltage stabilizing this Zener diode. In group I put, please prepare this Zener diode is important. Now, magnetic leakage, number of time I explain. Due to leakage, leakage plus means leakage reactance. Now, it is required to down because low impedance, low voltage drop inside means battery regulation, voltage regulation. Now, if higher value, there is another question. Higher value of voltage efficiency, higher value of efficiency and lower value of voltage regulation. Why we prefer? Correct, Because if lower value of voltage regulation, it means current is low, better terminal voltage, low losses, high performance of your equipment. Correct, motors generally. Then you have to draw the vector diagram. We have number of time we draw the vector diagram. Lot of time of transformer and alternator we give, please. Now running a three-phase motor, if one phase is open, then it is a single phasing. So we provide a single phasing due to what is the effect causes of single phasing? Heating, okay, of the motor. So rotor may be damaged because due to negative sequence component, slip is double, then copper losses are slip times of rotor input. Then this question we yesterday solved, this numerical of. Correct. Next is PN junction diode, and this recent today we solved this. EMF equation of AC generator we have explained. Okay, 4.445 F TP, KD KP. This question is number of times we solved. Okay, this alternate important question, please. Okay, so next is come to here this October month, September and October. So here is the you have transistor connected to common emitter. So yeah, same circuit, resistor, coupling and doubling capacitor. Just you check in Google or some electronic books, VK Mehta, there is this is given amplifier with common emitter. Same circuit will be there, okay, like this. It is a common emitter only. This I draw this circuit amplifier. Where we draw the circuit amplifier. Here, no? That is the common emitter only. And here operation of that circuit. Then block diagram briefly explains effect of negative voltage feedback in amplifier. Advantage of resulting of using the negative feedback. This intent is from amplifier only. Now this is okay. Main engine shaft driven arrangement for electronic system for frequency correction. Describe the operation of generator arrangement of this. So here it is like your governing control with the electronic circuit. Okay. Now part 2, list the factor to determine the starting torque of. Now it is asking the starting torque of three-phase induction motor TST equals to K E2 square K1 R2 by R2 square plus XX2 whole square. So here slip at starting, because at starting speed is 0, slip is 1. That's why here slip is disappear. Now it depends on what? This parameter you can write, or TST. As you know, this torque is proportional to your copper loss by slip, because it is P2. Okay. Then at starting, now this copper loss are starting of rotor current, TST square. Okay, R2 divided by slip. That is starting, slip is not there, the only it is directly proportional to your starting current and rotor circuit resistance. Then your power factor, starting power factor. Okay. Then you have to compare with full load torque. It is proportional to your full load current, I2 full load square by R2 by S. Now R2 cancel, full load slip. Then you have to divide this equation 1. This is the TST. This is full load torque, okay? So as you know, you please stable this TST by TFL equals to IST by IFL, rotor current of whole square into full load slip. This is the relation, and it is in with respect to percentage, like it is 150% or 200% of full load. Because you know starting current is high compared to full load current. That's why starting torque is higher than the full load torque. Okay. Next question. This motor numerical we solved. It is a wound rotor motor. I2 is given. Then he asked the resistance R2. I2 is given. So here actually we calculate rotor copper loss by this by subtracting this mechanical loss. Means we calculate P2 minus PM. This will give the rotor loss, first part. Then we calculate by this method I2 square R2 3 times. Then we get a R2 because we equate these two equations then. Okay. First you make this flow diagram, power flow diagram. You calculate this. Then this is also this also. Then you calculate a R2. This copper loss divided by 3 times of I2 square. Okay. This is the transformer, this phasor diagram we calculated. Now here it is simple, just you draw the star delta connection and write the star line voltage line current relation. Here there is a this by phasor diagram you can calculate this. Actually this question paper is tough. Easy also. Transformer question is hard. Motor also have a tricky question. This all numerical is tough. They are time consuming also. So please careful. Question selection is also very important. Next please. If we come to your this December month, recent month. काफी लोग इस क्वेश्चन को लेके परेशान हो रहे हैं. You have to forget about this. This time at least it is not appear. Repeat. Okay, this is already repeated. This is okay. I have shared. Means you draw the pump characteristics and system curve. When system curve and pump curve are intersect, you can calculate the motor rating for a particular flow rate. Actually here we draw the suppose there is a pump. So here flow rate, this is the flow, okay. Flow rate, it is in cubic meter per second generally. Okay, now it is coupled this impeller of pump. So it is coupled with motor. Yeah, this is your motor, okay. Motor. This motor draw the power from electrical mains. So here actually, motor side means, there is a input, motor input. This is your coupling. Then here motor output. And motor output means shaft power. This shaft output is pump output in hydraulic power. That is hydraulic power. Okay, so this hydraulic power is how we calculate. Very simple. Your flow rate in cubic per centimeter into density of what is the fluid here. Like it is water, then 1000 into your suction head, means discharge minus suction head, differential head. Okay. Hello. Here, because this pump is draw the water from, lift the water from somewhere. So what is the from baseline? What is the suction head? What is here? Discharge head. So this is a differential head. We take a total differential head. This is discharge minus suction. This will give you differential head. Okay. Into G. G is gravitational acceleration due to gravity. Divide by, it is 1000 to convert into kilowatt. If you not divide, it come in watt. So if you divide by 1000, you get a kilowatt hydraulic power. Okay. Then if there is a pump efficiency, you know. Then we know the motor efficiency here. Motor efficiency. So if this, now we calculate a shaft power, is the motor output. Motor output means shaft power, that is the HP rating. Then how we calculate this? Pump hydraulic power divided by pump efficiency, my dear. Okay, pump efficiency. Okay, hydraulic power by pump efficiency. Okay. Okay. Now you calculate, it is come in kilowatt. Now near about what is the power, what is the motor size available in market. We have to select that motor. This is give your motor selection. Okay. Now to calculate a flow rate, if we draw, this is your flow, means discharge at Q. Here it is head, we write head, pressure head, static head, okay, head. Or power also, head loss. So actually, the system curve is come like this due to your piping. And so there is a one dynamic head in, you know, when water is flow through this pipe, it develop a friction due to head loss. So system curve and dynamic curve, it will give, it comes like a combined curve. It is like this. This is called a system curve. Pumping system, pump system curve. And the head developed by the pump. Actually, not a pumping system. Pumping means connected pipe, elbows. They produce the resistance in the flow. So that's why head. This is the total head develop. Head occurs. It is a resistance to flow the result. Now pump develop a head. So this is the pump curve. This is your pump curve. This is system curve. When they intersect at a particular value, it is an operating point. Here we select the flow. Then corresponding to what is the power. So we see this power is accelerated here. Power means drawn by the motor or pump, required by the pump. Then we can calculate the power. Okay. Please see, I put in group. And efficiency, if you see, it is like this. So when efficiency, pump efficiency, it is like this. Okay. This is the efficiency of system. Okay. Got it? Pump and motor. They ask the motor selection for a pump. Okay. Now here, why it is important to maintain a high efficiency, values of voltage regulation. Now this is a speed control of DC motor. This question is here. You just is armature. In armature, you put a external resistance in armature circuit. Okay, and you calculate the EMF. Okay, so you know this for shunt motor, back EMF is directly proportional to. You calculate the back EMF, na EB equals to V minus IARA. So as the resistance is changed, then this I current is changed. Okay. Please you calculate this E1, IA1, RA1, EB2, V minus IA2, RA2. This will change. Then you know your speed is directly proportional to back EMF. You know, phi is constant here. So then we can write na N1 by N2 equals to EB1 by EB2. By this you can calculate the speed. Okay. Then same equation they ask. You draw the motor diagram. You just draw the motor and you write this equation, back EMF equation. And this is the your protection. Initial of the class we start from this only. So it is actually in DC how we detect the earth fault protection on DC system. There is a numerical is asked. Okay, earth lamp was there. Then again the equation of alternator and this numeric. Okay. So this month definitely question paper will be moderate. You please appear, be confident. Happy Makar Sankranti. Enjoy the festival today. Take a good sleep. And you please appear in the exams. Those have book or applied for examination in this month. Okay, best of luck.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Great.
Thank you, sir.
Thank you, sir.
Okay, huh? Thank you.
Sir, can you please scroll a little bit left?
Here. This you required.
Thank you, sir.
Right.